Homework 2, problem 12. For two co-moving charge plates, find the magnetic field everywhere. Find the magnetic force on the upper plate due to the magnetic field of the lower plate, and at what speed would the magnetic force balance out the electric force? Those are the questions we're going to look at. First, we look at the system, and here we have to realize that when I have a moving charge density, I actually have a current density, right? We've had that definition before. So this picture here is equivalent to having two plates with a surface current density on those two plates that goes in opposite directions. And so this would have surface current density K, and this would have surface current density minus K. And so we need to find, we're going to use superposition to do this, and so we need to find what the magnetic field due to a single planar system with surface current density K is. Let's look at an expanded view of a single plate. Let's choose a coordinate system such that the current is running in the J hat direction. And so we have current running in this direction. And then we're going to use Ampere's law in order to find the magnetic field due to this plate, this plane of surface current. The path that we'll use when we look at Ampere's law will be the following path. It will be a rectangular path that is perpendicular to the direction of the current, and so the surface will be like that. Surface will be like so. We will say that this has a distance L and a half height D, and it's going to stick up D both above and below the surface. For reasons of symmetry, we're going to argue that the magnetic field points only in the I hat direction, and we can go through a quick example of that. If we look at just two of the lines of current here, the magnetic field, so let's look halfway between these two lines of current, up some distance D. Okay, halfway between these two lines, we know that the magnetic field goes in perfect circles around these lines of current. And so if I try and draw those, I'm going to get something like that. At this point, I know that the current is going to point, or that the magnetic field will point that way for that line and that way for that line. The sum of those two is going to point sideways in the I hat direction. So I'm going to make the simplification, right, that the magnetic field is going to be equal to B sub x, which will only be a function of the distance D I hat. And that will be the simplification that I'm going to use going forward. For our little path here, so first let's write down what the integral form of Ampere's law is. It is that the integral around the edge of that surface ds of dl dot b is 1 over mu naught. 1 over mu naught is going to be equal to the surface integral ds d2x of n hat dot j, which is just the current enclosed. And so here this surface is going to be given for 4 different loops. On this top loop, this dl vector is going to be dx times I hat. On this loop going up, it'll be dz times k hat. On the loop going down, it will be minus dz times k hat. And on the loop here going sideways, it is minus dx times I hat. And furthermore, we're going to use one more identification, which is on the equally below the hoop, the magnetic field is going to point in the opposite direction. So B sub x of minus D is minus B sub x of D. And so using those simplifications, I can now evaluate the right-hand side. Since b sub x is only in the I hat direction, it won't contribute on the k hat parts of those. The rest of that, the right-hand side, the left-hand side is going to give me 2 times capital L 1 over mu naught times b sub x of d should equal to the total current that goes through, which is just our surface current K, but our surface current K, right, is going to be, our surface current K times the length L. So collecting everything, that's going to be that the vector B then, the function of position, is going to be equal to plus mu naught K over 2 I hat for z greater than 0, and we'll minus mu naught K over 2 I hat for z less than 0. Using this, we can now try to answer the first problem, which is what is the magnetic field everywhere? So first, what we'd like to do in order to answer that is just label the region. So we'll label the region above both plates 1, label the region between the two plates 2, and label the region below both plates 3. And so given that notation, we are just going to use the rules of superposition to find the magnetic field everywhere. And so for A, we're going to use that B total is going to be B for the positive plate plus the magnetic field for the negative plate. And so in region 1, we are above both plates, and so here we're going to say that the K for the positive plate, right, is just sigma V times I hat, J hat, right? And the K for the negative plate is sigma V times minus sigma V times J hat. So the total magnetic field in above both of them, I'm going to use the plus sign for both, and so this will be plus mu sigma V over 2 I hat. For the minus sign, I'm going to use the plus sign out front, then mu and minus sigma V over 2 I hat, which is going to give me 0. So in region 1, I get 0. In region 2, I do the same thing, but now I'm below the positive plate and above the negative plate. So I'm going to use the minus sign for the first one, positive sign for the second. So minus mu naught sigma V over 2 I hat plus mu naught minus sigma V over 2 I hat, which when we sum them together is going to give minus mu naught sigma V I hat. And so they combine in between, and in region 3 below, I'm going to use the minus for both of them. So minus mu naught sigma V over 2 I hat minus mu naught minus sigma V over 2 I hat. That again is going to equal 0. And so to summarize, my B total for the system is going to be minus mu naught sigma V I hat in region 2 and 0 otherwise. So that's the solution to part A. For part B, we are asked to find the force on the top plate due to the bottom plate. To do that, I'm going to use my general equation for magnetic force, This is just the integrated form of the Lorentz force. This is integral d3x of J cross B. Now for us, we know what the B due to the bottom plate is. We've already found that, so now we need J. J for the top plate is going to be fixed at one position, so we can use a delta function to define that. And so we can define this as plus sigma V, let's see, it's in the positive J hat direction, and then times delta of Z minus Z naught, where Z naught will be the position at which the plate is sitting. So just plugging that in along with the magnetic field that we already have for the bottom plate, we're going to get that the magnetic force is going to be equal to the integral. I'm going to break apart this d3x into d2x, and this is going to be in the xy plane, and then integral dz. Now for the j, I'm going to have sigma v times this delta function of z minus z naught. For the b, I am above the plate, so I'm going to get a positive mu naught, and then the k is minus sigma v over 2, and I still have left over from the j, I have a j hat and cross an I hat. So evaluating these, the integral of the delta function is just going to give 1, so that's going to go away. So that's going to give 1. The j hat cross I hat gives minus k hat, which is going to combine with that minus to give us a positive value. And then the integral over the xy, if I look at what this is, so if this is the plate, essentially what I'm looking at, right, is that area of the top. That's what this integral over xy is. It's the area. And so the magnetic force divided by area, so magnetic force per unit area, that's dividing this over to that side, is going to be then positive mu naught sigma squared v squared over 2 k hat. And so this force is, let's see, that's in the positive direction, so this is repulsive. To answer part C, it asks at what speed, part C, at what speed would the magnetic force balance the electric force? Well, to do that, we have to find the electric force per unit area. Again, what we're going to use is the integrated form of the Lorentz force, this time on the electric part. So F electric is the integral d3x of rho times E. Now, where E is due to the bottom plate and rho is the rho of the top plate. Now, the rho of our top plate, rho is a function of R, is going to be simply the sigma of the top plate times the delta function, same delta function as in the current density, delta Z minus Z naught. The E, we can look it up in our book. The E due to a plate is above the plate is going to be equal to the charge of the plate, so minus sigma over 2 epsilon naught, and this is going to be in the k hat direction, and the direction perpendicular to the surface of the plate. And so just plugging these in, we're going to get that the F electric is going to be equal to, again, integral d2x in the xy plane, integral dz of sigma delta z minus z naught times minus sigma over 2 epsilon naught k hat. Again, the delta function, the integral of a delta function is just going to give 1. This is going to give the area, and so this is going to give the electric force per unit area is equal to, let's see, minus sigma squared over 2 epsilon naught k hat. And so this is attractive. But now we need to make the comparison with our previous result. And so we're going to come here and look at what our previous result is. There's our previous result, and so copying that down, see, we can move this up. I want that F electric is equal to F magnetic, and that's going to give me that sigma squared over 2 epsilon naught, I'm dropping the minus and the k, is going to be equal to the mu naught sigma squared v squared over 2. Solving for v squared, right, we find that v squared should equal 1 over mu naught epsilon naught. And for those who have read ahead in the book, you realize that this 1 over mu naught epsilon naught is actually equal to the speed of light squared. And so there, the forces will balance them out if they are going at the speed of light.